On February 14th, 1990, a spacecraft 6 billion kilometers from Earth received an unusual command. It had not been asked to do science. It had not been asked to measure anything, to record any data, to perform any of the functions it was built for. It had been asked to turn around. For a machine in deep space, a machine traveling away from everything it had ever known at 64,000 kilometers per hour, turning around is not a trivial act. It costs fuel. It costs time. It interrupts the mission. And for a spacecraft that was already operating on borrowed resources, already stretching the limits of what its designers had thought possible, it was a request that some at NASA had argued against. They turned it around anyway. What Voyager 1 saw when it looked back has been described as haunting, as humbling, as one of the most important photographs ever taken. The man who convinced NASA to take it called it a mote of dust suspended in a sunbeam. But that description, as beautiful as it is, doesn't fully capture what happened in the moment that image was made. Because to understand what Voyager saw, to truly understand it, you first have to understand what Voyager had already been through. You have to understand the journey. Voyager 1 launched on September 5th, 1977. Not the first Voyager. Voyager 2 launched 16 days earlier on August 20th. But the one that would ultimately travel faster, go further, and become the most distant human-made object in history. The spacecraft itself is small. Embarrassingly small for something that has accomplished what it has accomplished. Its main body is roughly the size of a small car. Its iconic dish antenna, the high-gain antenna that it still uses to communicate with Earth, is 3.7 meters across, about the width of a parking space. Its total mass at launch was 825 kilograms. A grand piano weighs more. It was not built for permanence. It was built for a specific mission. Take advantage of a rare alignment of the outer planets, a configuration that occurs only once every 175 years, to fly by Jupiter, Saturn, and continue outward. The original mission planning documents did not contemplate what Voyager is doing now. The spacecraft was designed to last long enough to complete its planetary encounters. 5 years perhaps, 10 at the outside. It is now 47 years old and still transmitting. But in September 1977, none of that was known. What was known was the window. The planetary alignment, Jupiter, Saturn, Uranus, and Neptune arranged in a rough arc on the same side of the solar system, would allow a single spacecraft to use each planet's gravity as a slingshot, accelerating toward the next target without burning additional fuel. The trick is called a gravity assist. You approach a planet in a specific trajectory, the planet's gravity bends your path and accelerates you as you exit, and you leave faster than you arrived. Each planetary flyby added speed. Without the alignment, the journey to Neptune alone would have taken decades. With it, a single spacecraft could visit 4 planets in 12 years. The window opened in 1977. It will not open again until 2152. NASA sent 2 spacecraft. Voyager 1 was targeted toward Jupiter and Saturn, with particular emphasis on Saturn's moon Titan, a world shrouded in a thick orange atmosphere that scientists suspected might harbor complex chemistry. Voyager 2 was given a longer trajectory that would carry it past Uranus and Neptune as well. They left Earth 16 days apart. They would spend the next 13 years becoming the most well-traveled objects humanity had ever made. Voyager 1 reached Jupiter in March 1979. 17 months of travel through the void, 650 million kilometers from Earth, and then Jupiter. The images that came back rewrote every textbook that had been written about the outer solar system. Jupiter's Great Red Spot, photographed by previous missions as a static oval, turned out to be a roiling, churning maelstrom, a storm with internal structure, counter-rotating regions, boundary layers that moved at different speeds. The cloud bands that look smooth in low-resolution images dissolved at close range into intricate patterns of turbulence, waves, and eddies that no one had predicted. But the moon Io was the real shock. Before Voyager, Io was thought to be a dead, cratered rock, similar in character to our moon. The first close-approach images showed a surface unlike anything in the solar system. No craters. Instead, volcanoes. active, erupting volcanoes, mountains of sulfur, plains of frozen sulfur dioxide, a surface being constantly recycled by internal heat generated not by radioactive decay, as on Earth, but by tidal forces. Jupiter's immense gravity kneading Io's interior like dough, generating heat through friction. Io had been predicted to be volcanically active by a paper published 3 days before Voyager 1's closest approach to the Moon. 3 days. The prediction and the confirmation arrived almost simultaneously. Science doesn't often work that cleanly. That one did. Europa offered a different mystery. Its surface was not volcanic, but smooth. Suspiciously, impossibly smooth for a world that old. Smooth surfaces in the solar system mean geological activity, resurfacing, something filling in the craters that should accumulate over billions of years. The leading interpretation, tentative at the time, was a subsurface ocean. Liquid water beneath a shell of ice, kept liquid by the same tidal forces that were destroying Io from the inside. Europa became, almost overnight, one of the most scientifically important worlds in the solar system. A potential home for life, hidden beneath kilometers of ice, orbiting a gas giant 628 million kilometers from Earth. Voyager had found it in passing, in a handful of days of close observation while hurtling through the Jovian system at 35 kilometers per second. Then it was gone. Jupiter receding behind it, its gravity adding another boost to Voyager's already considerable speed. Ahead, Saturn. Voyager 1 reached Saturn in November 1980, 3.5 years after launch, 1.27 billion kilometers from Earth. At that distance, a radio signal traveling at the speed of light takes over an hour to arrive. Saturn's rings, seen from Earth through even the best telescopes, look smooth and uniform. 3 or 4 distinct bands, a gap here and there, clean. Almost simple. Voyager's cameras revealed thousands of rings, hundreds of thousands of individual ringlets, each on a slightly different orbit, each interacting with the others in ways that produced patterns that looked less like physics and more like music. Waves, braids, structures that had no right to exist according to the models available at the time. The ring system was not a simple disk of orbiting particles. It was a dynamic, constantly evolving structure of almost incomprehensible complexity. Titan was the primary target. Scientists had speculated for decades about Titan's atmosphere. Thick, orange, opaque. The question was what lay beneath it. Voyager's cameras could not see through the haze. The images of Titan's surface that mission planners had hoped for never materialized. The atmosphere that made Titan scientifically fascinating also made it visually impenetrable. What the instruments could measure was the atmosphere's composition. Primarily nitrogen, like Earth, with significant amounts of methane. Complex organic chemistry, a world that, if it were closer to the Sun, might have conditions similar to early Earth. Titan was cold, minus 179 degrees Celsius. But it was complex in ways that made scientists uncomfortable with the word dead. And then there was the decision. The close flyby of Titan that mission planners had designed for Voyager once sent the spacecraft on a trajectory that curved it out of the plane of the solar system. Most of the planets orbit roughly in the same flat disk, the ecliptic plane. Voyager 2 would continue within that plane, eventually reaching Uranus and Neptune. Voyager 1 would not. The Titan encounter bent its path sharply, throwing it upward out of the plane on a trajectory that would carry it away from every remaining planet in the solar system. There would be no more planetary encounters for Voyager 1. It would continue outward, upward, away, into regions of space no human instrument had ever penetrated, into a growing silence that would last not years, but decades. Saturn was the last planet it would ever see up close. The spacecraft was 9 years old when it passed Saturn's rings. It had another 35-plus years of travel ahead of it before the next significant milestone, and that milestone would not be a planet, or a moon, or anything so welcoming. It would be a boundary. Here is what traveling beyond Saturn means. At Jupiter, sunlight is 25 times dimmer than on Earth. Still visible, still measurable, still bright enough to cast faint shadows. At Saturn, it is 100 times dimmer than at Earth. At the distance Voyager traveled in the years after Saturn, crossing the orbits of Uranus, Neptune, the Kuiper belt, the Sun became a point, not a disk, a point of light, brighter than the stars around it, but not qualitatively different from them, bright enough to identify, but not bright enough to illuminate anything. The spacecraft was alone in a way that no terrestrial analogy can capture. Consider the distances. At the moment of the pale blue dot photograph, February 14, 1990, Voyager 1 was 6.06 billion kilometers from Earth. Light, the fastest thing in the universe, takes 5 hours and 35 minutes to cross that distance. A radio signal sent from Earth takes the same time. A response would take another 5 hours and 35 minutes to return. Any command sent to Voyager in 1990 required over 11 hours round trip. If something went wrong and the spacecraft needed immediate instructions, the word immediate had lost all meaning. And yet the connection held. Voyager's radio transmitter, operating on 23 watts of power, roughly the output of a dim refrigerator bulb, was still reaching Earth. The signal, attenuated by the distance to a fraction of a trillionth of a watt by the time it arrived, was still being picked up by the enormous dish antennas of NASA's Deep Space Network. The global array of radio telescopes positioned on 3 continents to maintain contact with deep space missions. The signal was real. The connection was real. But by 1990, Voyager had been traveling for 13 years and had not taken a photograph in a decade. Its cameras had been turned off after the Saturn encounter to conserve power. There was nothing out there to photograph. Nothing but void. And then Carl Sagan made his argument. Carl Sagan had been pushing the idea for years. He wanted Voyager to turn its cameras back on, point them toward the inner solar system, and photograph Earth from the edge of the solar system. Not for science, the image would contain no useful scientific data. Earth at that distance would be a point of light, barely distinguishable from stars, contributing nothing to what planetary scientists actually needed from the mission. Some at NASA considered the idea a waste of resources on a spacecraft with a finite power supply and a finite operational lifespan. Sagan's argument was not scientific. It was philosophical. He wanted the image because he believed humanity needed to see itself from the outside, to see with its own instruments what it looked like from a distance great enough to make everything seem small. Every war, every border, every empire, every king, every act of violence done in the name of territory, visible in one image as a fraction of a pixel on a mote of dust. He was right. But it took years to win the argument. In 1989, NASA approved the portrait. On February 14, 1990, Voyager 1's cameras were powered back on for the last time. The spacecraft was commanded to rotate, to point its cameras toward the inner solar system, and to take 60 photographs as it swept across the sky. A mosaic that would assemble into what NASA called the family portrait, the first image of our solar system taken from the outside. The photographs took 5.5 hours to reach Earth. When they arrived, scientists began assembling them into the mosaic. The sun dominated one end of the image, its light so intense that it scattered inside the camera optics, creating rays of light that spread outward. An artifact of the photography itself, not real. Most of the planets were visible as faint points. Some required significant processing to find. Earth appeared in one of the scattered light rays from the sun. A pale blue dot, roughly 0.12 pixels in diameter, smaller than the width of a single pixel. You could cover it with the tip of a pin. That dot is everything. Every human being who has ever lived was alive, or was born, or died on that dot. Every city ever built, every ocean ever sailed, every mountain ever climbed. The entire sum of human history, every war, every love, every discovery, every piece of music ever written, every meal ever cooked, contained in something smaller than can be properly measured. Sagan wrote his famous reflection on the image shortly after. He described it as a very small stage in a great cosmic arena. He described the rivers of blood spilled by commanders and kings so that in glory and triumph, they could become the momentary masters of a fraction of a dot. It is among the most quoted passages in the history of science communication. It is quoted so often that its content has, for many people, become familiar to the point of numbness. Don't let it be numb. Look at that image again. Not as a familiar thing, as the thing it actually is, a photograph taken by a machine 6 billion kilometers away, showing a planet that contains everything, reduced to something that cannot be properly seen. Here is what most people don't know about the pale blue dot photograph. The blue color is real. It is not artificially enhanced. It is not a processing artifact. Earth appears blue from 6 billion kilometers away because of the same reason it appears blue from low Earth orbit. The atmosphere scatters blue light, and the oceans absorb red and green wavelengths and reflect blue ones back. Even from the edge of the solar system, even reduced to a fraction of a pixel, Earth's specific chemical and physical character shows through. The dot is blue because Earth has water, because it has an oxygen-nitrogen atmosphere, because it is a specific kind of world, not just any rocky planet. Other planets in the family portrait are not blue. Venus, though it is similar in size to Earth, appears different. Its thick cloud cover of sulfuric acid reflects light differently. Mars is warmer in color, shifted toward red even at that resolution. The gas giants have their own subtle hues. Earth is blue, even from there, but here's the part that haunts. In 1990, Voyager 1 was 6 billion kilometers away. That sounds like a lot. And in human terms, in any terms that our bodies or our intuitions can process, it is an incomprehensible distance. You could not drive it. You could not fly it. No vehicle ever built for travel within Earth's atmosphere could reach it in a lifetime. And yet, 6 billion kilometers is still inside the solar system, not near the edge, not approaching the edge. The solar system extends, depending on where you draw the boundary, to somewhere between 18 billion and 100 billion kilometers from the Sun. The Oort cloud, the vast reservoir of comets that surrounds the solar system on all sides, extends up to 100,000 astronomical units, or roughly 15 trillion kilometers. At 6 billion kilometers, Voyager was deep in the solar system, still well within the bubble of our Sun's influence. Still, cosmically speaking, almost home. The nearest star to our Sun, Proxima Centauri, is 40 trillion kilometers away. Voyager, at the time of the photograph, had covered roughly 0.015% of the distance to the nearest star, not 15%. Not 1.5%, 0.015%. If that number doesn't make you feel something, read it again. The universe is not large in the way that large usually means. The universe is large in a way that makes every human conception of distance irrelevant. Voyager's journey, the most ambitious journey any human machine has ever undertaken, had, by the time of that photograph, barely begun. And Earth, already reduced to a fraction of a pixel from that early stage of the journey, was already invisible. After the family portrait, Voyager's cameras were turned off permanently. There was nothing more they could contribute. The power they consumed was needed elsewhere, for the instruments that were still doing science, measuring the properties of the space Voyager was traveling through, mapping the edges of the Sun's influence in ways no instrument had ever done before. Voyager continued outward. The years accumulated. The distance grew. In 2004, Voyager 1 reached the termination shock, the region where the solar wind, the constant stream of charged particles flowing outward from the Sun, slows down and heats up as it begins to collide with the interstellar medium. This was the first indication that Voyager was approaching the true edge of the heliosphere, the bubble of the Sun's influence. It took another 8 years. On August 25, 2012, Voyager 1 crossed the heliopause. The heliopause is the boundary where the solar wind stops, where the Sun's particles no longer dominate the environment, where the magnetic field shifts from one shaped by our star to one shaped by the galaxy at large. It is, by any meaningful definition, the edge of the solar system, the point beyond which you are no longer in any sense in the vicinity of our Sun. Scientists confirmed the crossing not immediately, but months later, after analyzing the data that Voyager had been transmitting. The moment of crossing was identified by a sudden and dramatic change in the particle environment. The density of high-energy particles from outside the solar system spiked, while the density of particles from the solar wind dropped. The magnetic field shifted direction. Voyager had entered interstellar space. It was the first time any human-made object had crossed that boundary. It was a historic moment in the exploration of the cosmos, a moment as significant in its way as the first airplane flight, the first satellite, the first human in space, the first steps on the moon. It was also, for most of the world, barely noticed. There was no camera to capture the crossing, no image to attach to the news story, no visual that could communicate what had happened. Voyager had traveled 35 years and 18.8 billion kilometers to reach a boundary that was invisible, that could only be measured by instruments that looked the same on either side. The universe does not provide ceremony for these moments. Voyager crossed into interstellar space and kept going at 17 kilometers per second. There is one more thing aboard Voyager 1 that has nothing to do with science. In 1977, before launch, a committee assembled by Carl Sagan, the same Carl Sagan who would later fight for the pale blue dot photograph, spent 14 months preparing a message. Not a message to NASA, not a mission brief, a message to whoever, or whatever, might one day find Voyager in the depths of interstellar space. The message is a golden record, literally golden, a 12-inch gold-plated copper disc sealed in a protective aluminum jacket affixed to the outside of the spacecraft. On its surface are encoded 115 images, greetings in 55 languages, music from cultures across the world, Bach, Beethoven, Chuck Berry, a Navajo night chant, a Pygmy girl's initiation song, a Georgian chorus, Azerbaijani bagpipes, Japanese shakuhachi, a Peruvian wedding song. And natural sounds from Earth: thunder, wind, surf, crickets, frogs, a wild dog, a mother's first words to her newborn child, the sound of a kiss. There are instructions for how to play the record engraved on the jacket, a diagram showing the correct rotation speed, a pulsar map giving Voyager's origin point, a hydrogen atom diagram as a universal unit of measurement. The record was designed for an audience that might be so different from us that language itself would be meaningless. So the designers used physics, mathematics, and the universal constants of nature as the starting vocabulary. The rest, the music, the sounds, the images, was an act of faith. Faith that something, somewhere, might listen. Faith that the cricket sounds, and the Bach, and the mother's first words might mean something to something that had never heard a cricket or a cello or a human voice. The record has been traveling for 47 years. Voyager is now over 24 billion kilometers from Earth. At Voyager's current speed, it will take approximately 40,000 years to make a close approach to another star system. Gliese 445. A red dwarf in the constellation Camelopardalis, toward which Voyager is currently, incidentally, aimed. In 40,000 years, the record will still be intact. Gold does not rust in the vacuum of space. The aluminum jacket will protect it from the slow radiation of the interstellar medium. The information it carries, the cricket sounds, the Bach, the mother's words, will still be there. No one alive today will know what happens to it. No civilization currently existing on Earth will be recognizable by the time it makes that approach. Humanity may not exist, and yet the record goes, carrying the sounds of a world that was briefly, improbably alive. There is a version of this story that ends with hope, with the idea that the pale blue dot photograph was a gift, a reminder of our smallness, a call to humility, a reason to take better care of the fragile dot we inhabit. And that is true. That is one of the things it is. But there is another version, a quieter one that the image itself insists on if you look at it long enough. On February 14, 1990, a spacecraft that had been traveling for 13 years looked back at its origin point and found it smaller than a pixel. Found everything, every human being, every city, every ocean, every act of love and violence and creation that had ever occurred, reduced to a fraction of a pale blue point of light, barely distinguishable from the scattered glow of the sun's rays and the camera optics. That photograph was taken 34 years ago. Since that photograph was taken, Voyager has traveled another 18 billion kilometers. Earth, from where Voyager is now, cannot be seen at all. Not even as a point. Not even with enhancement. The sun itself, our sun, the star that powers every living thing on this planet, is visible from Voyager's current position only as a bright star, brighter than the others. But a star. Not a sun, a star. That is where we are. That is how small the stage is. That is what the photograph was trying to tell us and what the continued journey has been confirming, kilometer by kilometer, year by year, in the 47 years since a small car-sized machine left Florida with a golden record bolted to its side and the sounds of Earth encoded in its cargo. The last thing Voyager saw before it left our solar system was a pale blue dot. And the blue meant water. It meant atmosphere. It meant life. It meant everything that has ever happened in the history of our species, compressed into something that could not be properly measured. And then Voyager turned away. And the dot was gone. And the spacecraft kept going, as it is still going right now as you watch this, outward, into interstellar space, into the silence between stars, carrying cricket sounds and Bach and a mother's first words into a darkness so vast and so old that the odds of anyone ever hearing them are, by any rational calculation, essentially zero. And we sent it anyway. That, more than the photograph, more than the distance, more than the science, is what haunts. We sent it anyway. If this made you feel the scale of where we are, subscribe. And I'll see you next time.